Can you hear me? Yes?
Yes.
Oh, okay, good. Okay, thank you. So welcome everyone to the seminar series for the Center for Signal and Information Processing. This center hosts really the faculty in ECE who really do research that relates to signal processing, information processing, machine learning within ECE. So this is really the ECE group with graduate students, and then we have really amazing staff members, Raquel, Janetta, Kathy, and Angel, that really help us run the show. We have been doing these seminars for CSIP since the late 1990s, and we have held them Fridays afternoon at 3 p.m. We used to have pizza, so we have more incentive for people to join. But now we don't really have virtual pizza, but hopefully soon enough, we will be able to have an in-person component to it. Not sure if we will have pizza, but at least there will be an in-person component for the seminars and a virtual component. And the idea in here of these seminars is really to host either people from outside campus, from outside ECE within campus, faculty members, graduate students, visitors, really kind of just to have really an informal kind of, friendly environment where we can learn about technical, work by others. And I take this opportunity to really encourage the graduate students that we have who are with us today on this Blue Jeans link today to really please, this is a very good practice for your conference presentations or defense or proposals or qualifying exam, whatever basically you are planning in a formal fashion. This is very good practice. So please speak with Huck. He has a very nice schedule. He will put you on the schedule, and that would be really a good way to practice. So, and then I want to really thank Raquel and Janetta from the staff and Huck, who really, we always rely on graduate students to organize these seminars, and we have always been doing that since the late 90s when I was a student. We want the graduate students to take ownership. They invite speakers, they talk with other faculty, with visitors, with the graduate students, and then they are the ones who really kind of run the show with great support from Raquel and Janetta in different logistical aspects of it. So please be supportive of Huck and the team. And if you have any speaker, even not yourself, if you have a speaker that you can think of, please just make the connection with Huck, and then he will take care of it. I think hopefully we will have, if not every week, but every we have an interruption with the pandemic, but I think now we are back to hopefully have this consistent seminar every Friday afternoon to end the week on a positive note and a friendly seminar. Raquel, anything else you want to share or mention?
No, that sounds good. For right now, we'll try next week to see if we can fill the gap with a DCT, but an email will come out about that later. But yeah, excellent. The seminars are a great way to start. It's a great way for everybody to practice their speeches, whether they're going to conferences or their defenses. I think it's a great idea.
And I see that you are ready with your polo shirt, the CSIP one, so I need to put mine on. Thank you, Raquel. Thank you so much, Huck. It's all yours.
Yeah, and we also see a lot of faculties here. Brett Anderson's here. Yeah. So yeah, and it's happy to have a lot of audience with the initialize from Gassam. So let me introduce Jun. So Jun is a final year's Ph.D. student at School of Electrical and Computer Engineering at Georgia Tech. So previously he worked in Microsoft Research, Mitsubishi Research Lab, and also Tencent Research Lab. So his background is speech recognition, but recently he working on Tensor, neural network, and model compression. And for today, he will give us a overview and big picture, and also his recent progress on quantum machine learning. So they all look like fancy, but Jun will give us in-depth and really introduction levels introduction. So welcome, Jun, and feel free to leave any questions in the chat. But please keep mute during this lecture. Yeah, and Jun will have a Q&A section after this talk. Appreciate it. Yeah, Jun, you can open your microphone.
Okay, can you hear me? Okay, I just want to show that the screen mode. Okay, let's get started. My topic today is about the quantum tensor network for machine learning and signal processing. I'm a final year Ph.D. candidate in the School of Electrical and Computer Engineering at Georgia Tech. So today's topic is divided in 4 parts. Firstly, I will show you the big picture about what's quantum computing, the significance of quantum computers. Then I will show you some fundamentals of quantum computing. Not so many people has the backgrounds of quantum mechanics, so I should give you some big picture about introduction about these fundamentals of quantum computing. Secondly, I will show our recent work about quantum neural network based on variational quantum circuit. I'll just show you our 2 important work. One is quantum reinforcement learning. Another one is speech recognition based on the quantum convolutional neural network. The third part is our most recent work. It's about quantum tensor network for machine learning. We just developed a new end-to-end learning framework for quantum neural network. It's a genuine quantum-based neural network without any other classical computation. So it's from the beginning to the end, it's just a quantum pipeline. I'll show you this work later, and finally I'll give you the conclusions. Okay, so let's get started. Firstly, I'll show the big picture about the significance of quantum computing. The next technology, I think, is quantum technology. Quantum technology represents the next quantum age. So we are in the information age. We have some new breakthrough information technologies. But next decades, we will see some breakthroughs in new energy, medicine, materials, science, and machine learning AI. So based on the new technology, we call it the quantum technologies based on quantum computers. And maybe some startups and IonQ is pushing this field forward. Google, IBM, and Microsoft also has unique technologies. And this is another picture about this market revenue about this quantum computing. And currently, we are in between the phase 1 and the phase 2. In the phase 1, because we don't have enough qubits, the number of qubits. So maybe we have to focus error reduction, how to reduce the quantum noise on quantum device. So, and at this time, we have the market revenue is about 2 to 5 billion all over the world. But this number can be rapidly increased to 25 billion in the next 2 or 3 years. At the end of this decade, maybe see this market revenue can be increased to $450 billion US. This is from the Boston Consulting Group analysis. So it means quantum computing, quantum technologies, quantum AI, other quantum finance. Maybe I'm guessing is a good research path in the near future. Currently, it's a time we have to practice our muscles, because in the near 5 to 10 years, maybe the quantum computer may get matured. So I think it's a high time practicing our quantum muscles. Okay, so this roadmap from IBM. IBM has this unique plan for creating some more advanced quantum computers. Currently, we are in the time 2021. At this time, IBM create a quantum computer called Eagle. Eagle means that it has a number of qubits about 127 qubits. Last year is only about 65, and this number can increase to 433 next year, maybe currently in the end of 2021. And next year we have a new IBM quantum machine has more than 100 qubits, has more than 400 qubits. But in the next 2 or 3 years, maybe the number can be increased to 1,000 qubits. And maybe after 3 years, the number can be as high as about 1 million qubits. So this is a very powerful quantum computing based on the IBM technologies. So this is the picture about the IBM quantum roadmap. Even though we have we only have 127 qubits, we can do some simple machine learning and simple finance work. But if we have more advanced quantum computers, more advanced technologies, such as natural sciences, optimization, combinatorial optimization, finance, and machine learning, can be available. More advanced such topics can be done by using such more advanced quantum computers. So I'm very optimistic towards this direction. Okay, this IBM this year it currently has IBM Q experience. It's on the cloud. We can use the IBM quantum computer to simulate many machine learning tasks. Currently, it has so many 16 qubit quantum machine, and there is 2 or 3 64 qubit machine, but it's always busy. So always we just use a 16 qubit machine to simulate our experiments. But the number of qubits can be over 1,000 in about 3 years. So it is currently we just use 16 qubits, and in about 3 years we can use more advanced quantum technologies because they have more than 1,000 qubits. And so Google and Microsoft has a different plan for creating their unique quantum computers. Google maybe is about in 2016 they built 9 qubit quantum computers. About in 2019 they announced their quantum advantage because it has 72 qubit quantum computers. This year they realized 54 qubits with quantum noise error correction. It's a big through for the quantum technologies because that's 54 qubits are algorithmic qubits instead of physical qubits because it has realized noise error correction. Microsoft has a different plan because they are based on topological qubits. Topological qubits, they announced that it's a natural way to implement fault-tolerant qubits and gates. So they said it's a more noise robust quantum technologies than superconducting qubits based on the Microsoft topological qubits. Okay, this is the big picture about significance of quantum computing. It has the market revenue is so high, different companies have different optimistic plan to create more advanced quantum computers. Okay, let's show some fundamentals of quantum computing. It's very related to quantum mechanics. So what's the difference between the quantum computer and the classical computer? For a quantum computer, it's considered 2 important characteristics. One is a superposition, and another one is entanglement. Superposition means that there's a quantum state that's in between 2 basic states. So for classical bit, maybe the classical bit means it's either in the K0 or K1. K0 means the first element is a 0. K1 means that the second element is 0 or is 1. There's nothing in between. But for quantum state, for quantum bit, for one qubit quantum state, we call it a qubit. It means that there's something in between. C0 and C1 is maybe in the domain of from 0 to 1, and we can realize something between because they do some linear combination of to the K0 and K1, and the whole this quantum state in the two-dimensional Hilbert space. What's another particular characteristic is do the measurement. If we do the measure the quantum state, we can find this K0 with a probability of C0 per square. But if you also can find the quantum state can be collapsed to K1 with a probability with C1 square. So if we do the measurement, it immediately comes to a bit. So this property we call the superposition. Okay, this picture shows one example. The superposition is a cat positive, another one is a cat negative. Just equally assign the probability to cat 1 and cat 0. Okay, another important property we call is entanglement. Quantum entanglement is a physical phenomenon that occurs within a pair group of particles in such a way that if we observe the particle A, we can understand the particle B, because particle A and particle B are totally entangled. For example, particle A spins clockwise, then particle B will spin counterclockwise around the same axis. So if the particle A and particle B are entangled, it does no matter how far the distance between particle A and particle B, if we measure the A, we directly understand some quantitative states for the particle B. There's a very unique characteristic. We call it the quantum entanglement. Okay, another big difference between the classical computer and the quantum computer is the quantum computer relies on a totally different universal case. No matter how difficult the program for quantum computer, for classical computer, maybe it's the program can map to classical case, the combination of different combination of classical case. But for quantum program, it maps to the combination of quantum gates for qubits. Another difference is that for each universal quantum gate, it is associated with the unitary matrix. Unitary matrix is spectral matrix, and then we can see for the signal gate, it has a unitary matrix, but for some rotation gates, it has associated with the cosine, sine, some very different, very complicated matrix. But this matrix, we can show that it's a unitary matrix because it satisfies some linear algebra property. Okay. So another topic we show is a quantum system with D-combined qubits. Just now we consider the 1 qubit. But we have a system that has more than 1 qubit. We have a D-combined qubits. What's it look like? So for vector D-dimensional vector. So the corresponding quantum state is a D-qubit quantum state, can be seen as the tensor product of 1 qubit quantum state. And this in the tensor product of 2-dimensional hyperbolic space. Another important thing is that the computational power of such a quantum computer can double with any new qubit. So if there is only one element, it's a 2-dimensional vector, but you consider 2-dimensional vector and it's corresponding to the 2 qubit quantum state is corresponding to the 4-dimensional vector, and it has a more powerful representation power. If I add some new qubit in the system, the computation power can be doubled. So you have more than 2 qubits. This leads to the exponential growth of computational power. Another important thing is if such a system, we see the D-dimensional qubit quantum state, we see if for 2 qubit state are entangled, it can be computed by the linear combination of a tensor product of 1 qubit states, but it cannot can be decomposed the tensor product of 1 qubit states. So this is an important mathematical property for quantum entanglement. Okay, so this picture shows the quantum advantage. Quantum advantage is Google announced their quantum advantage for two waves. The first wave just found that means that quantum algorithms with polynomial complexity more likely to be part of the first wave quantum advantage. So for some traditional NP hard problem, and we can find some new quantum algorithms to make such NP hard problem become polynomial solvable. For example, for some RSA public key cryptography, for some traditional computing, it's difficult to find the private key based on the public key. Because maybe you have the B length is more than it's over 4,000. If you want to find the private key, it takes about age of the universe. But for a quantum computer, it's quite different. It takes about approximately 1 hour to break the cryptocurrency. So this is a very unique property for quantum computers. It has an exponential speed up to solve so many traditional secured problems. For example, the RSA key cryptography. That is a very important advantage for the quantum computer. The second advantage for quantum computer is that it has a quadratic speed up for solve so many combinatorial optimization problems. For example, for some traveling salesman problem, it has realized a quadratic speed up to find some feasible solutions. So this is very important for some work in finance. For example, we do some Markov chain Monte Carlo sampling. It's maybe traditionally it takes about 1 hour to find some solution to finish the simulation. But if we use a quantum computer, the time maybe it can reduce to 10 minutes because it has a quadratic speed up for such a if we use a quantum computer. Okay, this quantum computer is quite important for financial engineering. In the finance of money, business companies are very common with quantum computing, and very focus this the power of quantum computing because there's so many technologies can be used in quantum computing. For example, the Monte Carlo do the risk analysis. It can use amplitude estimation to realize some quadratic speed up for some portfolio optimization. There's so many quantum algorithms correspond to such a portfolio optimization. But here we just focus on the machine learning, supervised machine learning, and supervised. And today we focus on deep learning. We just developing some new algorithms for quantum neural networks. So this talk, we just focus the quantum neural networks. We have shown our recent work about quantum reinforcement learning, quantum speech recognition, and our new quantum learning pipeline. Okay, let's get started to the second part. So in this part, we show our recent work about quantum neural network based on the variational quantum circuit. The first thing I'll just show how to bridge between the deep neural network and the quantum neural network. So everyone may be very clear that deep learning has succeeded in many domains. For example, speech recognition, biology, deep reinforcement learning. Last year, my group has released one paper, the use of the deep learning to estimate for some various communication to do the channel estimation. Okay, also very popular. This may be the foundation in the domain of computer vision. But here is on to unboxing the techniques from the classical neural networks. You can see that empirical study about the classical neural network is very fast. It's faster than the theoretical study about why this deep neural network can work so well in practice. But such a theoretical understanding about the classical neural network can help us to understand the quantum neural network, because currently it is an empirical study and theoretical study and in the same pace. So maybe some theoretical study about the traditional neural network can help us to better understand how to scale such a quantum neural network. But here we just today's work, we just focus on variational quantum circuit. But we use the variational quantum circuit instead of such a very complicated quantum neural network. The reason is that we have to consider this current NISQ devices. NISQ means the quantum noise intermediate scale quantum devices. So because we do have a large number of qubits to spare for the error correction, so we have to suffer from the quantum noise get involved. So we have to use a very special architecture to go against such a quantum noise, and maybe the performance can be maintained by using such quantum architecture. But in the future, maybe it's more quantum qubits, more qubits can be available. We can set up more complicated architectures. Okay, so the current work we based on the variational quantum circuit to realize the quantum neural network. The basic architecture of a variational quantum circuit can be divided into 3 parts. Maybe the first part, we call it quantum embedding generation. Quantum embedding generation is used to convert the classical data into quantum states. The second part is the variational quantum circuit. In this part, the component has some adjustable parameters. If we do the machine learning work, we have to fine-tune the parameters. So in this part, there are some parameters can be adjustable based on the training data. And finally, we do the measurement. Measurement means that we want to collapse the quantum states into classical states. So we want to destroy the superposition and super entanglement. We want to convert the quantum states back to the classical data. We want to use the classical data to do some post-processing. It's a basic architecture about the quantum VQC-based quantum neural network. The training power size for VQC-based QN model is very easy because it's an interaction between the CPU and the GPU. CPU just control these optimization algorithms, and QPU just plays the content such a quantum neural network. If you want to update the parameters during the training power size. After that, if you want to convert back the classical data to the CPU, and CPU may do some control work, maybe to change the algorithms and to use a different the learning rate, different algorithms to update the parameters stored in the QPU, the models stored in the QPU. So this is a basic idea about the architecture and about variational quantum circuit and the training power size just based on interaction between the CPU and the QPU. And CPU just control this optimization algorithm, and the QPU just store the parameters and to update the parameters. The basic architecture and basic training power size for quantum neural network. Okay, just a very interesting advertisement for our work. So in 2019, okay, this paper is published in 2020, but before this year, in 2019, we have released our recent paper. This paper is based on it's called Variational Quantum Circuits for Deep Reinforcement Learning. We call it's the first paper about using the VQC, the Variational Quantum Circuit for Deep Reinforcement Learning. And in 2019, we just released our course. Because of this work, we have awarded the first prize in Sanandu AI Quantum Machine Learning competition. So this because our unique contribution of the use of this VQC-based quantum computing, quantum architecture on a real quantum computers. because at that time is only have a few qubits, and these NISQ devices. We devise such architecture to run some machine learning models on such architecture. It's a very unique contribution. So we get such as Shenandoah AM quantum machine learning competition is the first prize for us. Okay, so next we'll show the details about quantum reinforcement learning. Quantum reinforcement. So this picture shows this slide shows that the basic ideas of deep Q learning. Deep Q learning is want to based on the current state, the current action. We'll look at some Q learning table to find the return values. But for deep Q learning means that we want to use the deep neural network to replace such a Q learning table, such that based on different state, it has a correspond to different the Q value action. So this we use such a equation 3 to update the parameters in the deep neural network. So this is a basic idea. For the VQC-based quantum neural network, we want to replace such architecture, the deep neural network, with the quantum neural network. So the basic idea is quite similar to such as deep Q learning, but one major difference that we use the quantum neural network to replace such architecture. We just use such architecture, use this architecture to replace this deep neural network and other the machine learning optimization algorithms is basically the same. So we just simulate our architecture on very simple thousand lake experiment. For such a simulation, we can use a very DP algorithm to very easy to find the best solution. But if we use such as a thousand lake simulation, such environment, we want to test whether or not our new architecture can work so well in practice, because we have a very limited qubits as input. So we'll see whether or not such architecture can work so well. So eventually, after about 300 episodes, it can get converged. At this epoch, you can find the best solution. So in this work, we will show that empirically verify that even though we use the VQC-based quantum neural network, you can eventually to find the best solution. So you can empirically verify that our VQC-based QN can work so well in practice. It's the significance of this work. Okay, next at the same year, we also released a new work based on the quantum convolutional neural network for automatic speech recognition. Also, this is the first work use the quantum technology for automatic speech recognition. Nowadays, the speech recognition is end-to-end system. The input is the time series speech. Output is the transcript associated with the speech. But here we just to set up want to set up a vertical federated learning architecture, and to use the quantum convolutional neural network to extract the quantum convolutional speech features. Such speech features can be stored on the cloud. And if we want to do the speech recognition, we can just read the speech as input, with the output from the cloud, and the outputs of cloud will output some the quantum convolutional features as the input to such an end-to-end speech recognition system, and the output is the transcript associated with the features. So this work has been released, and some codes have been opened to public. And what's the significance of this work? We show that if we use the quantum convolutional layer to output some feature, we can see that the feature is more meaningful compared with the conventional features based on the classical convolutional neural network. So if we use quantum convolutional encoded features, it has the more differentiable and meaningful compared with the traditional convolutional encoded features. And the results actually correspond to our observation. We show that we use the quantum features plus recurrent neural network pipeline. We see that our performance, the speech recognition accuracy can be increased from the it has some slight increase, but here we use a different pipeline. I see the increase can be increased to 55.12. This number. Okay, this I think this at that time is the best result we achieved based on the quantum convolutional neural network as a feature extraction, and use the traditional pipeline, the RN pipeline, as the Kusen model to do the speech recognition. But this year we have a new result. It means a new Bayesian result come out in this year ICAS paper. Okay, this the second work. We use the convolutional neural network as a feature extractor for speech recognition. Next, we just show our recent work. It's based on the quantum tensor network for machine learning. And the key technology we used is called tensor tree network. Okay, so what's a tensor tree network? Tensor tree network provides a compact tensor representation for a traditional neural network. So this the graphical representation of a tensor tree network. For a classical feed-forward neural network, any feed-forward neural network can be represented as the tensor tree representation associated with such a feed-forward neural network by using the tensor tree decomposition. What's the benefit of tensor tree decomposition is that in our paper, in our theoretical paper, we will show that the tensor tree network can maintain the representation power of a neural network. It means that even though we use another format to represent, such as the feed-forward neural network, the Bayesian performance can be maintained. But the benefit is that we can use much fewer model parameters get involved in such as a tensor tree network, but the performance can be maintained. In our work, we can somehow to improve such a feed-forward neural network. Most importantly, a tensor tree network can physically find an equivalent substitute, a quantum substitute, to assign it in a quantum computer. It means that we use a quantum tensor tree network or other tensor network. Any tensor network can be placed in a quantum computer because we can find equivalent quantum implementation to realize such as a tensor model. That's a very important property. Why? Because for a classical feed-forward neural network, other recurrent neural network, convolutional neural network, it's intractable to place such a model on quantum computer. If we use a quantum computer, there's no way to place such a model on quantum computer to simulate the result. But if we can to convert the format or transform the format into the tensor tree format, we can find we can convert such a feed-forward neural network on a quantum computer. We can simulate quantum computer by using the tensor tree representation for such the traditional neural network. This is significance. I think the most important significance for the tensor tree network to represent the classical neural network. So this I have several work about this to empirically or theoretically to show the representation power of tensor tree neural network for represent the deep neural network. So here we're just using tensor tree decomposition to each tensor layer of the classical neural network. We call the new model as the tensor tree deep DN instead of the classical DN. And also because we always use the speech data, we just test our performance on speech recognition performance to see the performance of speech recognition. So in our last year ICAS paper, we show that if we use a tensor trained deep neural network, we use a much less model parameters, but we can maintain the baseline performance. The baseline performance based on the PASQ. PASQ is a metric for the speech enhancement. The larger PASQ score means that the better enhance and the better quality of enhanced speech. So this the baseline performance of 2.86, and use the similar architecture. Use the tensor train architecture to represent such a baseline architecture. The baseline can be basically maintained. But if you use other experiments show that other use more than one channel, use 2 channel and 8 channels, the result shows that it can maintain the baseline performance of the counterparts. So this one evidence to show that if the tensor train neural network can maintain this the empirical performance of deep neural network. Another one is that in this year we have some new paper about tensor train DN for speech recognition. You can greatly improve the baseline performance to a lower level, whatever level. So this is the best performance we achieve. So even though we use a much fewer model parameters, the baseline can be improved even if we use a tensor train representation for the fully connected layers. Okay, this is the contribution we achieved. We want to show that the basic idea, we want to show that the tensor train can maintain the representation power of neural network, because tensor train network can be implemented on real quantum computer. But for the classical neural network, there's no way to place it in the quantum computer. So if the tensor train representation for the classical neural network can maintain performance, we can firstly to convert the classical model into the tensor train format. After that, we can place the tensor train network on quantum network, on a quantum computer. So we can indirectly to simulate the performance of classical neural network on quantum computer. This is significance we use the quantum tensor train network in this part. So in this idea, this is our new machine learning paper about we just set up the quantum tensor network enhanced recursive architecture. We call this a genuine end-to-end learning framework for quantum neural network, because we don't consider the classical neural network at all. We just all the architecture, all the trainable, all the framework, all the frameworks are based on the quantum architecture instead of classical architecture get involved. Because currently we use a limited number of qubits. So the first step always is to do the dimension reduction, because we input always a high dimensional input, but we have the limited number of qubits to represent the input. So we have to do the dimension reduction to a smaller dimension. After that, we have to encode the classical data into the quantum states. So the first step is how to do the dimension reduction. But traditionally, based on the classical neural network, that's there to do that. But here we just implement the tensor train network. The tensor train network can be, as I said, can be placed on quantum computer. So for such architecture based on the tensor train network for feature dimension reduction is totally totally quantum end-to-end learning framework. Okay, there's another important part in our work that we call it the quantum tensor encoding. Quantum tensor encoding just convert the classical input into the quantum states. And here in our work, we show that if we use only very simple poly-wide rotation gates, to realize, such as the quantum encoding, quantum embedding. But the most important part is that we use the tensor train network instead of the denser layer to realize a genuine quantum end-to-end learning framework. And second side, we just follow by such as quantum tensor encoding to convert from the classical data into the quantum states. So after gets the outputs for the quantum tensor encoding is that the quantum embedding. Quantum embedding can be seen as the quantum features as the input to this as the input to this variational quantum circuit. So in the training process, we just update the parameters of the variational quantum circuit. Okay, this is a theoretical understanding about representation power of the quantum tensor network-based VQC. Based on the classical universal approximation theory proposed by Sabanko in 1993, we can show that the representation power is mainly determined by this dimension reduction part. But in our theory, we just show that the tensor train network and the dense layer has the same representation power because they share the same upper bound. Here we show that. So even though we use the tensor train network to do the feature reduction, but it has the same the performance can be maintained if we don't use the dense layer. This is a theoretical understanding of if we use a tensor train network instead of a dense layer for the feature dimension reduction. Okay, so some of experimental results for such a work have been shown in our release account paper, and our simulation highlights the advantage of such architecture based on the QTN-VQC. Currently, we are still implementing a variational quantum tensor train network, such that the genuine end-to-end quantum model can be realized in practice. It means in the next few months, we will see our new implementation based on the VQC and TTN instead of current TTN architecture. It's our future work. Okay, this gives us a conclusion to this talk. In this talk, we just give you some big picture about quantum computers and quantum mechanics. Secondly, we just show our recent work about variational quantum reinforcement learning based on the variational quantum circuit. And thirdly, I just introduce our quantum convolutional neural network for automatic speech recognition. The last part, we show that if we use the tensor train network, we can bridge between the classical neural network and the quantum neural network, and how to place the classical neural network on real quantum computers by using tensor train network, by using tensor train decomposition. And lastly, show the basic architecture. Our quantum tensor network-based VQC is the end-to-end learning framework for quantum neural network. We have to do that. Currently, we are studying about how to implement a variational quantum circuit for implementing a new tensor train network. It's our future work. Okay, this is the end of my talk. Our source codes for our projects are partly released in our GitHub repo. For example, some tensor train network is implemented by myself, and the quantum speech recognition, and these are implemented by Hawk. And currently, our quantum tensor network VQC the source code will release soon. Also, we are open to some academic and industrial collaboration at GT and all the communities. If you have interested to do some joint work, we will have interested to organize some workshop, conferences, special sessions, please contact me by sending me email. This year we have Hawk and I we jointly organize EJK tutorial. The topic is about quantum neural network for speech and NLP. And the next year in ICAS paper, we have a special session based on the quantum machine learning for speech and language processing. we also have some new proposals for some tutorials in some AI and speech conferences and some workshops. So we in future we see we very welcome to more work will come in the quantum computing, quantum machine learning domains. Okay, it's the end of my talk today. Thank you so much.
Right. So thank you, Jun, and thank you all the audience to be with us for over 50 minutes. So we already have some enthusiastic questions from the audience. So yeah, the first question is from Professor Anderson. So I think it's maybe it's too fast like over this talk, but one main interest for all the audience could be what is the quantum advantage when we apply on the speech problem. For example, at the very beginning, we look at some optimization property. But Jun, could you just briefly summarize why could be the quantum advantage if you apply this computing on speech or image feature, for example, in terms of representation power or in terms of security? Yeah, please.
Okay. We think Haq maybe has a better understanding about this question. So from my understanding, in this work, we just implement for the written learning architecture. This is related to the security. Maybe it's we use the more secure feature when it's a quantum, maybe it's encrypted somehow to do that. Okay, it's more secured feature stored on cloud. And another advantage we see that is a more representative for speech signals. It's for example, you can compare the two pictures, two spectrogram. You can see that the quantum convolutional encoded features more meaningful than this the classical convolutional encoded features.
Let me add one sentence to this question. So originally, we think about the problem could be how can we use a render encoder for applying a certain kind of problem. For example, if we have end-to-end processing, mostly the customer privacy or data have some leakage issues by having queuing-based perturbation or visit. So this work is mainly trying to use a render encoder, and by selecting this render encoder, we find out this quantum embedding have a better representation in terms of acoustic feature. So that's the motivation is still starting from the security property, but in the meanwhile, we find out this embedding have a better representation. And how this representation can be clarified, they have some recent work to discuss this representation. But in the really basic understanding, you can think of if we cast a binary data to a quantum space, there should be you cast a binary data from XY axis to a ball. So the feature space can be much richer. And the quantum data means the encoding and this angle inside this ball. So recently people find out this representation can be much rich than binary domain data. Hope this quick answer reserve the first questions. Anderson? Yeah, and right, so we have the second questions.
So the other part of my question was when we're training something like this network, neural networks have local extrema, and so training is never going to yield something that's optimal. Do we get around some of that with quantum computing?
Okay, it's about
right. So yeah, I can add something. So since we have fewer trainable parameter, so one thing this presentation didn't show up is they need much fewer training apples to find a local minima. But it's hard to guarantee the minima is the global minima. But empirically, if you only have a few parameters to tune with a trainable architecture, say with the circuits like the neural network, but only have a few of a parameter like the gate to tune, so it's much easier to converge. But is that really the global minima? I think it's an open question. Yeah.
Okay, I think this related to the representation of such the quantum neural network based on the variational quantum circuit. For such as the quantum encoding part, okay, this operator is a linear operator because there's a matrix, the transformation matrix totally is a unitary linear operator. And the variational quantum circuit is also is a unitary linear operator. So from the perspective of optimization, even though if you have a very perfect quantum computer, the training process become much easier compared with the training a classical neural network. And this is from the perspective of the optimization, because if we can only consider the quantum embedding combined with the variational quantum circuit, is equivalent to the linear operator. So this want to do the very similar to the linear transformation from input to the output. So the optimization become much easier, but because of the quantum noise get involved, so this the training cannot maybe so in practice if you want to place our model on real quantum computers, there's so many quantum noise involved in such a system. So there's some it's a terminology called the barren plateau as for the training a neural network. Barren plateau means that it's you can trap to your local optimal point, and maybe the performance can be degraded. So this because of the quantum
sorry,
noise.
we still have two questions, and maybe you
Okay.
reply David by email offline. So we still have two questions, one from Nargis, one from Dylan. So the first question from Nargis is about the advantage of quantum reinforced learning. So I think you didn't show this parameter saving, right? Or you have some comment on their questions in the chat room. Yeah.
Okay. So one of the advantages that we just save a lot of parameters. Here we just use you can call the number. For each alpha is a parameter, beta is a parameter, gamma is a parameter. Totally we use only 12. 12 free parameters. These free parameters can be adjustable. So instead of the classical neural network, maybe thousands or millions of parameters using the deep Q learning. We just use a very that's a 12. Maybe it's use a much deeper layer. It's about 24 or 36 free parameters in this model. So we just use a few model parameters in such as architecture. Another one is maybe the physical meaning is quite different. And we just to adjust the qubit rotation angles and to train the model. So this is quite different from the classical neural network. But here, this model sparsity is a very important issue.
Yeah, and I think another question is from Jillian. So Jillian have a comment on the tensor chain architecture selection, or maybe Jillian, since you are here, maybe you can add more comments. Hi, Jillian.
Hi, so yeah, very nice talk, thank you. So I use tensor networks to study quantum wave functions. And in this setting, like we have tensor trains, but we also use like much more sophisticated versions of these tensor networks.
Yes.
Like 2D versions of tensor trains, as well as like multi-scale tensor networks. Have you thought about using anything like this in your work? Would it be useful? I'm just curious.
Okay. So first important thing, you're welcome to read our recent paper about this tensor chain network. Okay. The second one, so you use a 2D tensor chain network. It's very interesting. You have given me some paper and see that currently maybe it's I just see there's a one-dimensional tensor chain network. Okay, maybe so use a two-dimensional tensor chain network. We can have a better representative power, I guess. for such, the reason we choose the tensor train network in this work because it's very simple compared with our very complicated tensor networks. You know, I understand there's more complicated tensor networks, but it means that we have to use more qubits to implement such an architecture. But in our work, we even use a very simple tensor train network. We can maintain the representation and generalization powers of a classical neural network. So we just choose this simple architecture instead of very complicated tensor networks.
Okay, thank you. The 2D version, we call it a PEPS, in case you want to look it up. So projected entangled pair states. It comes from physics, but yeah.
Okay.
Thank you.
Oh, thank you for your suggestion. I think it is very interesting you to consider 2D version of tensor train networks.
Yeah, and I think this project is just open, and maybe you guys can have some collaboration. Yeah. So, any audience have some questions?
Excuse me. Can I have a question, please?
Please.
Okay, no problem.
First of all, thank you so much. It's a great talk, and it's wonderful. So I have a very, maybe it's a naive question. So could you explain a little bit more about the tensor train network? So how does this, correct me if I'm wrong, so because I just mentioned is one of the job that the TTN does is to do the dimensionality reduction, right? Because usually you'll have for a general in a general problem we have a sort of a high dimensional input, but given the limited resource of the quantum computing, right? The quantum computing system, we have to reduce the dimensionality of the input to this extent. So my question is, could you explain a little bit more about in what sense does this is the dimension reduced by this TTN?
Okay, so your question, how to implement the dimension reduction by using the TTN, right?
Yes, or it will be great if you can provide maybe a illustrative or a toy example.
Okay. All right, very easy to understand this one. Maybe you understand you use a tensor layer, use a matrix to do the dimension reduction from high dimensional input to the low dimensional output, right? So TTN can use such an architecture to best represent, to give you the tensor train represent to such a matrix. You can see there's a fully connected layer, a dense layer as a matrix. We can use a tensor train decomposition to such a matrix. So we just tensor train decompose such a matrix, but the input and the output can reshape back to the one-dimensional vector. We're only concerned with the tensor input and tensor output. After get get tensor output, we can reshape the tensor train representation back to the one-dimensional vector. So in the future, if we release our codes, you can see how to implement this. But now, just to give you the high-level understanding about it, we just has a tensor train representation for such a tensor layer, and the input and output can shape into the tensor format or can shape back into the one-dimensional representation.
So is it like in the beginning we have a vector, right, input, right? So it's like everything is working in parallel, and so but after the transformation of TTN, we sort of put the working pipeline into the sequential way, right? Can I understand in that way?
Yeah. Okay, maybe the TTN just implemented in a parallel way. It's in a parallel way, and it's instead of the sequential way, it's a parallel way, and the output can be combined, can be returned back to a one-dimensional vector, because output is just the output from the different paths, different parallel paths. So we have to combine them together into one path. We call it this step as a reshape into one-dimensional vector. That is a high-level understanding about how to implement, such as using tensor train network to do the dimension reduction. The key idea is that we just convert the tensor layer into the tensor train format, but somehow we can convert the output tensor train format back to the one-dimensional vector.
Okay, I'm sorry. So, but the last follow-up question at this point is,
okay.
So is a TTN reversible? So is this transformation reversible?
Okay, that's a good question. For current architecture, it's not reversible for such architecture. So that's the reason we have to implement this VQC-based TTN. We can see that we have to do work. To do work means a variational quantum tensor train network. Okay, we just want to okay. It's we have to implement it using the variational quantum circuit to find the quantum substitute for such a tensor train network.
Gotcha. So can I say that can I sort of relate the TTN to, let's say, the PCA, right? So we sort of we do the truncation, eigen truncation with PCA. So we lose some information in the linear combination in a linear sense. And similarly to the TTN, we also essentially we're going to lose some sort of information at this part.
Okay. Yes. But currently, because it's non-reversible, so we lose some information.
Gotcha.
So, but between this work, we just shows that if we it has the same representation power if we use the tensor layer and we use if we use the TTN. So even though we use the TTN to replace the tensor layer, the performance can be maintained. But both architecture can lose some information. So just a motivation we use how to implement the VQC-based TTN. If you have such an architecture, the conversion to the the dimension reduction between the high dimension vector down to the low dimension vector is totally reversible as no information loss in such a framework. So, and in doing so, we have maybe can further improve our performance.
Okay.
Yeah. Thank you for your question.
Yeah. Thank you so much.
Yeah, and thank you everyone for staying here right now. And what I just want to say, 2 weeks after we still have this seminar, and we have invited a partner applied scientist from Microsoft Research to give us a talk. And stay tuned on the CSIP series. And if you have more questions, you can stay here, and I will end the recording. And thank you everyone.